Hi everyone, we're going to graph a rose, and here's our equation, and before we graph it we're going to do 3 tests to check for symmetry so it's easier to graph and we only have to do part of a table. So the first test we're going to take is the polar axis test. See if it's symmetric to the polar axis. So we're going to replace theta with negative theta, and we get, so you're replacing theta with negative theta, and we're going to get r equals 2 cos of 2 times negative theta. Cosine's an even function, so basically that negative goes away, and it is symmetric because these two match up here. So when you play, it's just like we did with even and odd functions before. So it's symmetric to the polar axis. Now, for the y-axis, or the line theta equals pi over 2, we're going to replace theta with pi minus theta. So I get r equals 2 cos of 2 times pi minus theta, and this yields 2 cos of 2 pi minus 2 theta. And if you do your sum and difference, well, we're doing the difference identities for cosine, and we get 2 cos of 2 pi cos of 2 theta plus sine 2 pi times sine of 2 theta. This is just 0. Cosine of 2 pi is 1. So we get r equals 2 times cosine of 2 theta, because this is just 0, and that knocks all that out. Alright, so basically it is satisfied. This passes, and this passes as well. And now we want to see if it's symmetric to the origin or the pole, and it's not going to be, because, well, it actually is. It's going to say it's not. But the pole, basically what you can say is, when you put the r in, and like we do with the pole, we put the r in, and you notice that r squared, or negative r, sorry, put in negative r, equals 2 cos of 2 theta. Does not equal our original. But basically, if it's symmetric to both the polar axis and the line, so basically the x-axis and the y-axis, then yes, it is symmetric to the pole. It's kind of like our cubic function, like this. So this is symmetric to the origin, and it can flip over. So if it flips over, you flip it over, then it's symmetric to the x. Then if you flip it over again, it's symmetric to the y. So it's kind of that same principle there. Alright, so since it's symmetric to both, I really could shorten my table. I only use quadrant 1. And then I'm just going to graph from there. So basically I plugged everything in. It's pretty easy. I'm going to graph this. So I'm going from pi over 2 goes to negative 2. So we're going down to negative 2 right here. And then pi over 3 is negative 1. So that's going to go here. Here's your 3. So that's going to go there. And then at pi over 4, it's at 0. And at pi over 6, it's at 1. And at zeros, it's at 2 again. So basically, I'm going to connect these like this. All right. Then from there, you can do it both ways, but basically what I do is I'm going to make it symmetric first to my polar axis, and I'm just going to kind of draw it in. I'm also going to make it symmetric to my y-axis, so I try to draw that in. I'm not being precise here because I just don't want to be. All right, and then since it's also symmetric to the origin, this part's symmetric to the y, it's going out by 2, right? So I can make it here, and I also can make it go out to here, and there it is. You can get more precise if you want to mess with the ordered pairs and things like that. All right, so there it is. Here's some information about it. They're characterized by simple equation with a, where a is not 0, and you have some n's. So I did some n's here. Here we have 3. Here we have 2. So a lot of times graphing these is a lot of knowing what the equation looks like. It makes it a lot easier. So this one would be a rose with 3 petals. So something like this. And this one would be a rose with 4 petals like we just did. All right? When your argument is 2 theta. And again, we'll do some more of these problems where we have to graph them and we can see some differences. Thank you and have a nice day. Bye-bye.